When we look at the sheer unbelievable progress of modern artificial intelligence, it's incredibly tempting to assume it's all just a matter of scale. We naturally think, right, if you want a machine to be smarter, you just throw more hardware at it. You feed it more electricity, you buy more servers, you build it bigger, and boom, you get a smarter AI. It feels like a straightforward math problem. But, as we're going to dive into today, the reality of engineering a digital mind is far, far more complicated. It's heavily bottlenecked, and honestly, it's incredibly precarious. Building a smarter AI isn't just a simple matter of stacking more layers on top of each other.
See, we naturally think that to build a better artificial brain, we just build the tower taller. You add another floor of processing, you add more parameters, more complexity, and you'd expect the machine to inherently get smarter. But here's the catch. Mathematics has a strict breaking point. In fact, back in the 1990s and early 2000s, early AI researchers were absolutely stumped by this. Every single time they tried to stack neural networks deeper than just a few rudimentary layers, the math simply shattered. It literally created a multi-year dark age for deep learning because, well, gravity always wins. Eventually, the mathematical structure inherently suffocates under its own massive weight. When you stack too many layers on top of one another, the machine doesn't just fail to get smarter, it completely, catastrophically breaks down.
And that leads us to a fascinating, deeply counterintuitive question. A question that haunted top-tier researchers for decades. Why does expanding an AI's physical capacity for knowledge actually trigger total amnesia? We all would think, that a bigger brain equates to better memory. But instead, creating vertical depth causes the entire system to forget how to absorb new information. It entirely breaks our common-sense understanding of how computers are supposed to work.
Welcome to the Overview Effect, where you zoom out and everything changes. Today, we are going on a journey to look at the deeply hidden, entirely brilliant architectural hacks that prevent modern deep learning networks from collapsing in on themselves. We're going to crack open the black box of artificial intelligence and look closely at the mathematical scaffolding that's barely keeping these models alive. Let's get into it.
Okay, so to build this from the ground up and achieve true emergent intelligence, engineers start with our attention mechanisms. Now, you can think of these mechanisms as complex mathematical filters that figure out how individual words relate to one another in a sentence. Engineers take these filters and they stack them directly on top of one another. This creates a towering vertical architecture. And honestly, this stacking process is exactly what puts the deep into deep learning. Every single layer takes raw data, extracts a slightly deeper, kind of more abstract meaning, and then passes it upward to the next floor of the tower to be analyzed all over again.
But here is where things go terribly wrong. When this deeply stacked machine tries to learn from a mistake during its training phase, the architecture turns against itself. Let's say the model makes an incorrect prediction. It calculates that mathematical error and has to send a correction signal backward through the network to fix its behavior for next time. This vital learning signal has to cascade from the very top penthouse of the architecture, traveling an enormous, grueling mathematical distance, all the way down to the foundational lobby. And it has to do this just so every single layer can adjust its parameters. We call this the downward signal.
And this right here brilliantly illustrates the core mechanical failure of deep networks. It's a phenomenon called the vanishing gradient problem. Think of these architectural layers as a vertical stack of thick, exceptionally dry sponges. The correction signal is poured from the very top. That first layer, the top sponge, soaks up a massive amount of the signal. It greedily absorbs all the math required to fix the immediate error, leaving almost nothing for the foundational logic below. It passes whatever tiny remainder is left down the chain, and the middle layers get, well, mere drops. By the time that crucial, lifeblood learning signal finally reaches the foundational blocks at the bottom of the tower, they are left completely bone dry.
Let's just pause on that for a second because it's absolutely crucial. Because the foundational layers receive essentially zero correction signal, they sit in total silence. They are entirely unable to update their weights, they can't correct their assumptions, and they cannot learn from the mistake. If the foundation cannot learn basic logic, the higher layers are forced to build highly complex concepts on top of a fundamentally broken, rotting base. This means the bottom of the network decays and the machine's overall intelligence hits a permanent, unbreakable ceiling. So, paradoxically, the taller we build the artificial mind, the faster its foundation dies.
So, the multi-billion-dollar question is, how do we fix the plumbing of this building? Well, to save the network, engineers designed something incredibly clever called shortcut connections. Previously, the old architecture forced every single piece of data, and every fragile learning signal to take the stairs through every single dense, heavy processing layer, and of course getting diluted along the way. But shortcut connections, they act as an express elevator. They completely bypass those heavy, greedy blocks, dropping pristine, full-strength learning signals straight down to the foundational layers. Because of this brilliant little bypass, the bottom of the tower finally remembers how to learn.
But, and there's always a but in computer science, right? Solving this amnesia problem creates a second, equally dangerous threat. As raw data flows upward through these new express elevators during normal operation, the numbers tend to become wild, unstable, and incredibly dangerous. Because they are now bypassing the dense mathematical filtering layers that normally keep things in check, the numerical values can compound and inflate rapidly. A tiny, unfiltered calculation can snowball exponentially, threatening to entirely derail the system and completely crash the computer's memory.
To wrangle this wild instability, the architecture uses a secondary, highly specialized mechanism inside each block called a feed-forward network. Now you can think of this like a massively expanding microscope. It takes the mathematical geometry for a single word, or token, and violently inflates its dimensions. We're talking about blowing it up from maybe hundreds of data points to over thousands, easily making it 4 times its original size. It dramatically expands the network's view to intentionally search for tiny, hidden mathematical flaws, inconsistencies, and patterns that might cause a crash later on.
Now, what's really fascinating is what happens while the data is stretched out under that massive microscope. The machine applies a very specific mathematical function called the GELU, or Gaussian Error Linear Unit. Basically, this is a nonlinear activation curve. See, instead of relying on rigid, straight lines, which, let's face it, computers naturally prefer, this curve gives the artificial brain its nuance. Think about it. Human language is messy. It contains sarcasm, poetry, slang, and emotion. It just doesn't work in rigid, straight-line binary logic. This specific curve allows the network to actually model the complex, curvy, messy reality of human thought.
All right, so once the machine finishes inspecting these massive ballooned details and successfully applies its curved, nonlinear logic, it carefully removes the microscope, it shrinks the data perfectly back into its exact original dimensions and slides it safely back into the flow of traffic. The data is now entirely stabilized. It has gained incredible contextual insight, but has safely lost its dangerous exponential weight, and it's finally ready to move up to the next floor of the tower. But here is where we hit a really profound realization in this whole explainer. A perfectly designed brain is completely useless until it experiences the world. You could take all these brilliant components we just talked about, assemble a perfectly engineered 124 million parameter tower connected to a massive cluster of supercomputers and burn thousands of dollars in electricity to run it today. But if you turn it on right now and ask it to generate a simple sentence, it will output total, random, incoherent gibberish.
It's kind of tragic, really. We spend years perfecting the architecture of the mind, only to realize we had built an empty room. All of these brilliant structural hacks we just covered, the express elevators, the volume dials, the expanding microscopes, they contain zero actual knowledge. None. They do not hold historical facts, they do not understand grammar, and they certainly don't know what the sky looks like. They merely create a hollow mathematical vessel where intelligence is logically allowed to survive once it is eventually introduced.
And this brings us to the final, absolutely essential step, pre-training. It is only by training this foundational architecture on massive amounts of unlabeled text that the magic actually happens. Imagine forcing this pristine, empty room to read every book in every library on Earth 10 times over. It consumes trillions of words from articles, code bases, and just raw internet data. Through this unbelievable, frankly mind-boggling scale of consumption, adjusting its millions of parameters by constantly trying to predict just the next word, it finally furnishes that empty room. That is how it transforms into a generative assistant capable of writing a structured poem or debugging your code. So when you really look past the illusion and the sheer magic of a conversational language model, you start to realize what it truly is. It's not some omniscient, all-knowing brain, nor is it a magical thinking box. It is just a deeply fragile tower held together by brilliant mathematical scaffolding. It is constantly balancing on the razor's edge of total collapse, kept alive only by these hidden architectural tricks that engineers fought for decades to discover.
If this explainer changed how you see things and helped you grasp the incredible engineering balancing act inside modern AI, hit that subscribe button for the overview effect. Thank you so much for joining us on this journey, and we will see you in the next one. But before you go, ask yourself, if human intelligence relies on forgetting to stay sane, is it possible our artificial towers are actually remembering too much?
Think about it.